Hello there, young physicists. Have you ever wondered why electrical devices like heaters and toasters get hot when switched on? Well, today we are diving into the fascinating heating effect of electric current, also called Joule's heating. Here's a fun thought: why did the electron go to therapy? Because it felt resistance. Now, when an electric current passes through a resistor, the resistor doesn't just let electrons zip through freely, it resists their flow, kind of like how a narrow corridor slows down a crowd. This resistance causes some of the electrical energy to transform into heat, warming up the resistor. This warming is what we call Joule's heating, and it's quantified by the formula H equals I² multiplied by R and T, where H is the heat produced in joules, I is the current in amperes, R is the resistance in ohms, and T is the time in seconds for which the current flows. Notice how if you increase the current, resistance, or the duration, the heat produced also increases. According to Joule's law of heating, the heat generated is directly proportional to the square of the current, the resistance, and the time. So, in simple terms, more current or resistance or longer time means more heat. This is why your phone charger doesn't get hot quickly, but a toaster gets really warm. It has a high resistance and often a larger current running through it. Let's keep this idea flowing as we explore exactly how this all adds up mathematically. Alright, time to put on our physics detective hats and unpack where the heat formula comes from. Imagine an electric current I flowing through a resistor for time t. The work done by this current can be expressed as W equals V times I times t, where V is voltage in volts, I is current in amperes, and t is time in seconds. But wait, by Ohm's law we know that voltage V equals current I times resistance R, right? So, substituting V with I times R, our work done becomes W equals I times R times T, which simplifies neatly to I² multiplied by R multiplied by T. This work done by the current doesn't just disappear, it transforms fully into heat within the resistive material. That means heat produced H equals I²RT. Keep in mind, this neat derivation assumes all the electrical energy turns into heat and none goes into mechanical work or light. It's like all the energy is playing in the resistor's thermal sandbox. So, this formula isn't just a magic trick, it's grounded in solid physics connecting electrical work and heat generation. Let's zoom in on what really drives the heat generated in a circuit: current and resistance. The heat produced rises steeply with current because heat is proportional to current squared. That means if you double the current, the heat produced shoots up by 4 times, like turning a stove's knob twice as much and suddenly your pan is blazing. For a fixed current, materials that have higher resistance produce more heat. Think of them as the traffic jams for electrons, causing more energy to convert into heat. This quadratic relationship with current and direct relation with resistance is the hidden reason why fuses and electric heaters work. Fuse wires are designed thin and with the right resistance so they heat up and melt when current gets too high, cutting off electricity to keep devices safe. Electric heaters, on the other hand, cleverly use materials with high resistance to produce warmth efficiently. So, understanding how current and resistance control heat helps engineers design safer and more effective electrical circuits. Now, where do you find Joule's heating making your life cozy and convenient? Loads of everyday gadgets. Think electric irons that smooth wrinkles by converting electric current into heat with their resistive plates. Geysers that warm your bath water rely on this heating effect to transform electricity into thermal energy. Toasters crisp your bread by passing current through their resistive wires until they glow hot. Even electric bulbs use this principle, where the filament, usually tungsten due to its high melting point, gets hot and emits light without burning out immediately. Speaking of safety, Fuses protect circuits by melting when too much current flows, thanks to the heat generated by the thin wire elements. Imagine the fuse as a policeman who breaks the circuit if things get too heated, literally. In the diagram, you can picture a thin fuse wire connecting a circuit. If excess current causes too much heat, this wire melts, stopping electricity flow and averting damage. These examples show how the heating effect of electric current is not just science theory, it's working hard in our homes every day. Let's tackle a classic calculation to see Joule's law in action. Suppose you have a resistor with resistance 5 ohms and a current of 2 amperes flows through it for 10 minutes. How much heat does the resistor produce? First, convert the time into seconds since our formula needs that. 10 minutes times 60 gives 600 seconds. Next, recall the heat formula. Heat equals current squared times resistance times time. Plug in the values. 2 amperes squared is 4, multiplied by 5 ohms gives 20, and then multiplied by 600 seconds equals 12,000 joules. So, the resistor produces 12,000 joules of heat in that period. This makes sense physically. As the resistor has moderate resistance and current, it burns a significant amount of heat over that 10-minute time frame. Understanding these calculations helps us predict and manage heat in electrical devices safely and effectively. To wrap up, the heating effect of electric current is all about converting electrical energy into heat inside resistive materials. The key formula we learned is heat equals current squared times resistance times time. Using Ohm's law, it can also be expressed as heat equals voltage squared times time divided by resistance. Work done by current in the circuit, given by voltage times current times time, appears entirely as heat, energy conservation in action. Joule's law tells us that heat varies directly with the square of current, resistance, and the duration of current flow, so even a small increase in current can cause a big jump in heat. That's why devices carrying high currents need thick wires to keep them cool. We also saw how fuses and heaters put this principle to practical use. Fuses protect circuits by melting under excessive current, while heaters generate warmth on purpose. So, next time you see a glowing toaster or a buzzing iron, remember the physics of Joule heating at work. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.